In this episode, we're going to be finding out how to get an 1,000-mile range battery, just what's going on with EV battery fires, and what technologies we should be pinning our hopes on for those super energy-dense batteries. But today, the Mercedes EQS, with its 107.8 kilowatt-hour batteries and 452 miles of range, is the longest range EV currently on the market. And whilst that's not 1,000 miles, I think that would have come as a bit of a shock to John Goodenough, the co-developer of the lithium-ion battery, who in 1980 achieved a staggering 4 volts in that very lab there, doubling the work of Stanley Whittingham. Akira Yoshino built on Goodenough's work, and in 1991 the lithium-ion battery entered the mainstream market in a Sony camcorder. And today they power devices, store our energy, power electric vehicles, and scientists at the Institute of Physics in China claim that they've achieved an energy density 9 times greater than that revolutionary Sony device. So what happens next? Just how good can batteries get? In a lithium-ion battery, when the cell is charging, lithium ions move from the cathode to the anode across an electrolyte. Meanwhile, the electrons move separately in a circuit. When the cell is discharging, i.e. when it's being used, the process is reversed and the electrons generate a current. The battery cells can be made from different ingredients, and particularly the cathode, and that's where we start to hear various different names. So for example, NMC, nickel, manganese, cobalt, and LFP, lithium iron phosphate. And the anodes are generally made from graphite, and a lot of EVs currently available today may be made from one of these two chemistries.
If you like the Fully Charged Show, you will love our Everything Electric exhibitions around the world.
Next up, Everything Electric Australia
and Everything Electric London.
Get your tickets today.
Making batteries more energy dense comes down to how much lithium can be squished into a cell. But it's not easy to pick a single battery chemistry winner, as it depends what criteria you're comparing. For example, NMC versus LFP. NMC is more energy dense, i.e. has a greater number of kilowatt hours per kilo, but LFP is cheaper and has greater thermal stability. So we enlisted the help of battery expert Dr Euan McTurk to guide us through this chemistry conundrum. But to kick us off, the big burning question: just how worried do we really need to be about EV battery fires?
So the most flammable chemistry in an electric vehicle today is lithium nickel manganese cobalt oxide, NMC, which is found in your long-range electric vehicles, and is the only chemistry that's offered by some manufacturers. However, even that, in an absolute worst-case scenario, your odds of that vehicle catching fire, and that's the vehicle, not just the battery, catching fire, are between 20 and 60 times less than a petrol or diesel car. And the reason for that is because the oxygen within the cathode, so it's lithium iron phosphate, 8 means as oxygen, means that even if you were to drill straight through it with a big metal rod and short it all out, the oxygen is so tightly bounded that, yes, it's going to self-discharge very quickly, that cell, and yes, it's going to cause some decomposition and venting of hot gas, but the odds of that reaching the passenger cabin, by the way, are infinitesimally small, such as the way that the car is designed. Let's just be clear on that. Point is that because there's so little oxygen coming out, it just doesn't catch fire. And in fact, the likes of the blade cells from BYD, which are used not just in BYD's electric cars, but in the standard range Tesla Model Y that's built in Berlin, those cells are LFP, but if you drill straight through them when they're fully charged, they don't even get that hot. They get to like 60 degrees C. They don't vent any gas. They basically just go, don't do that again. People who keep worrying about absolute worst case scenarios, like genuinely an EV like NMC fire in a worst case scenario, the odds of it happening are incredibly small. And if it does happen, it's not like a ruptured fuel tank where it's an instant cremation for everyone in the vicinity and any surrounding cars. Because a battery pack is made up of lots of individual cells, then it's one that would fail. And eventually the heat from that would cause another one to fail, and so on. So it'd be lots of mini fireworks, effectively, over a prolonged period of time, which means that you, as the occupants and the passers-by, have plenty of time to vacate the vicinity. So there's developments on this coming all the time, but with this move towards solid state, particularly your kind of ceramic style solid state, which is non-flammable, and I believe QuantumScape's one of the leaders in that regard, and the move towards the likes of lithium iron phosphate, which is just so docile that it's actually used as a firewall in the hybrid battery design by Our Next Energy, One Energy, most battery fires you see are from very cheaply made consumer electronics and e-scooters and hoverboards that are bought on, like some dodgy website somewhere. The cell chemistries and the cell quality and the production quality and so on are nothing in comparison to the meticulous standards that are used in electric vehicles. It's a totally different thing. It is chalk and cheese. It's there's no wonder basically some of those cells would catch fire, how badly they would be made in comparison to an electric vehicle where it's incredibly robustly manufactured, tested to destruction, and managed by the control electronics and the liquid cooling system in the vehicle as well.
Reading about any vehicle fire is unnerving, but with the statistical likelihood so low, hopefully fears can be allayed. Now on to our big battery breakthroughs. What's up first?
One of the arguably most important trends at the moment is increasing affordability, and that's where sodium ion is so important.
So sodium ion, that's instead of having lithium ions, we've got sodium ions.
To an extent, yeah. I mean, they are broadly similar, but then you kind of lift the lid on them a bit, and there are important differences. So, for example, lithium ions can very happily pigeonhole themselves in between the sheets of graphene that make up a graphite anode in a lithium ion cell. If sodium ions try to do that, they are bigger and more cumbersome, and they actually smash the layers apart because they're too big. So, a bit like a dog that still thinks it's a puppy, and it just still tries to climb up on you. So you need to use disorganized hard carbon instead of graphite. So, broadly the same material, but in a different structure. But the other clever party piece it has is that you can safely discharge a sodium ion cell all the way down to 0 volts, ship it halfway around the world and recharge it and use it safely. So not only is it much cheaper to make, it's much cheaper and safer to ship, which means that you're looking at about a 30% cost reduction for EV batteries or energy storage batteries.
But we also know that it's not necessarily as energy dense as, say, its kind of lithium ion counterparts. So, are we ultimately going to see it in vehicles? Is that where it should be?
Some of the energy densities aren't quite as good as what we would expect from even the likes of lithium iron phosphate, which is the lower end of the kind of broad church of lithium ion chemistries that are used in EVs today. But that's still plenty for grid storage and for static energy storage at home. You're not as constrained by the volume that you can fit the battery into. So that makes absolute perfect sense for grid storage. Incidentally, as well, sodium ion doesn't mind being outside as much. It doesn't mind cold weather as much as lithium iron phosphate. It doesn't lose as much range. It doesn't need as much thermal management. It's actually a far easier cell to look after. But that said, we are seeing signs that we could get energy densities that are approaching lithium iron phosphate, and that's why we're going to start seeing them in electric vehicles as well, for your kind of standard range / city cars at the very least.
Made from truly abundant salt and with no nickel, no cobalt and no copper, this safe, cheap chemistry has a lot going for it. But it's unlikely to break any range records. So what's our next contender?
Solid state, much like lithium ion, is a broad church, and we're starting to see various different chemistries being developed which have their pros and cons. So there's some that are made of ceramics, which tend to promote very fast charging and discharging, but the issue with them is that they tend to be a bit brittle. So if you're driving, for example, a solid state equipped electric taxi on the cobbled streets of Dundee, then you're going to be breaking that thing to bits after a while. Whereas polymer electrolytes, solid electrolytes, are much more flexible. So they would be up for that challenge. However, the kinetics are not as good. In other words, they don't allow lithium ions through as quickly as ceramics, which means that the discharge rate is a bit slow, which arguably should be okay for discharging because, if you're looking at a range of several hundred miles, the C rate, in other words, the power that the motor's drawing versus the capacity of the battery pack, is going to be very low. So that maximum discharge rate is not going to be huge. But if you want to rapid charge it quickly, that's where you're going to be sitting staring at your watch for a bit. But in theory, we could start to see very long ranges and very quick charging without needing any kind of increase in temperature to make them work at their optimal range. That's another issue with solid state. Sometimes they require a slight increase in temperature, say 30 to 50 degrees C, to get them to behave at their optimum.
I mean, they seem a bit tricky. Why are they kind of regarded as this almost sort of utopia battery state?
It's because they are kind of regarded as the holy grail, because depending on the exact chemistry, you get doubling of range per charge at least. You get the non-flammability, particularly with the likes of ceramic electrolytes and so on. So you've removed polymer, which is plasticky and potentially could catch fire, and you've removed a liquid electrolyte, which is very flammable, and you've replaced it with something that is not flammable, and that's vastly improved your safety. Charging times, there's some startups that are talking about sub 15 minutes from 10 to 80%, which is your typical sort of motorway rapid charge. You're looking at the ability to do away with bulky anode materials and potentially use a pure lithium anode. If you manage to combine all of the strengths of all of the different broad church of solid-state electrolytes, you end up with this holy grail. But we are still a bit away from that commercially, but there's exciting progress being made.
We're unlikely to see pure solid state until 2025 or even 2030 for mass market use. And whilst there are some examples of semi-solid state in vehicles today, surely there are other interim chemistries that perhaps are a little less tricky to engineer.
I would definitely say silicon anodes for that. It's a really good, not just interim solution until solid state, but something that would be very attractive in its own right.
So adding in, if I've got this correct, so adding in silicon to the anode side, which means that you can hold more lithium, therefore could be much more energy dense. However, what I've also read is that in having the silicon, so whilst that can become more energy dense, it also has a bit of a Violet Beauregard moment where it totally expands, or a sumo suit moment perhaps, which could damage the cell and then obviously cause those things like short circuiting. So is that the thing that's preventing this from being possible, and how much benefit does the silicon give you anyway?
So silicon anodes, in theory, are a huge improvement on graphite. So for graphite anodes, you need 6 carbon atoms just to house 1 lithium ion. With a silicon anode, 1 silicon atom can house 4 lithium atoms. So you're looking at about a 10 times increase in energy density on the anode side. You've got to factor in that once you build it at to cell level, once you put in the separator and the cathode and things like that, it's not a 10 times increase, but it is about a doubling of energy density. That's gravimetric and volumetric, weight and volume. So a doubling of the range of an electric vehicle for some of the more advanced silicon chemistries that we're seeing at the moment. But the issue with silicon, as you rightly pointed out, is that it expands up to 300% as it's being filled with lithium ions during charging. So this means that, the cell physically expands and contracts because the anode's expanding and contracting, and it physically starts to break itself apart. And that means that you obviously lose vast swathes of your, of your active material as you end up with these kind of icebergs calving, from the main body of the anode, and that just becomes electrically kind of lost in the system. But there are a couple of interim solutions that have been deployed. So silicon has been successfully deployed as almost like a sprinkling of fairy dust into graphite anodes to help boost the range. And in fact, the likes of Panasonic has been doing that with Tesla batteries for a good few years now. So we've seen modest increases in energy density as a result of that. But there are some very clever solutions to stop this expansion and contraction, or to accommodate it. So there are some companies that have developed a graphene corset that goes around the silicon anode and stops it from expanding even though it wants to, and it holds it in. And then the other one, which is really quite clever, is Amprius, arguably one of the leaders in the silicon anode space. They've got silicon nanowires, so you've almost got like a forest of nanowires that are lined up on the current collector, and they can expand and contract without smashing into each other. It's been designed in a way that there's a huge surface area for lithium to be able to get in and out of the silicon anode without physically expanding to the point that it breaks itself apart.
There are a bunch of companies across the world racing for their silicon to be in vehicles in the very near future. Amprius even claims to have reached the illustrious 450 kilowatt hour per kilo mark, meaning that this could be the solution to enable electric flight. And whilst it could double EV range, isn't the more exciting prospect the chance to make batteries smaller and lighter?
Very true. It would certainly put an end to this whole thing about, electric cars are going to collapse all of our car parks and rip up our roads and things, which of course are articles that are written by people who drive 2.7 ton petrol Range Rovers, not 1.8 ton Tesla Model 3. So I mean, it would just help to further bolster the fact that EVs are getting lighter, and their range is definitely getting better. But part of that can be driven by efficiency through lighter weight and a smaller footprint, rather than going for big bloated SUVs. Yeah, very much off topic, but yet somehow very much on topic at the same time when it comes to batteries.
Tackle that expansion problem, and silicon anodes hold a lot of promise. But what else have we got?
Lithium sulfur, which again is of interest to the aerospace industry because it's so lightweight. Sulfur we have an absolute abundance of from oil refining, from desulfurization. So we've got these big yellow mountains that we gradually work our way through, but it's cheap, it's abundant. And we're like, oh, what else can we do with this? Turns out that it can be, in theory, a very effective cathode material. So the way that it works is that you have these polysulfide chains, so lots of sulfur kind of joined together. And as the cell is discharging, lithium ions bookend those polysulfide chains, which then get smaller and smaller and smaller as they start to accommodate more lithium ions. They kind of break off them, and you end up eventually with 2 lithium ions and a sulfur. So yeah, that's how that works. And then obviously the opposite happens on charging. The issue with lithium sulfur is that it quite loves that whole kind of polysulfide shuttle, if you wish. So basically, even if you've disconnected the cell and you're no longer charging or discharging it, sulfur from the cathode might go across and try and pick up some more lithium and then continue to discharge itself. So the polysulfides shuttle across to as close as they can get to the anode and go, right, you'll do, and take a lithium ion with them. With lithium sulfur, you're looking at a high rate of self-discharge as well, but we have already found applications where that doesn't matter as much, because if you are charging it and then using that battery within a couple of hours and then taking it back to home or your depot and then charging it and using it again the next day, then it doesn't really matter. So it's the likes of aerospace, because it's so light. Now, that's a very good point. The gravimetric energy density of lithium sulfur is much higher. So in other words, you get much more energy per weight, per kilogram. That said, the volumetric energy density is broadly similar to lithium ion today. So the actual physical volume of the pack would be similar, but it would just be very light. And that's why aerospace is interested in it, because you are looking at north of 400 watt hours per kilogram.
Lithium sulfur is another super lightweight option that we may see powering electric flight, even though it doesn't necessarily come with the volumetric density benefits seen with silicon. But there is still work to do to tackle that polysulfide shuttle and scale up this chemistry. So is there something readily available now that's slightly less cantankerous?
So I would say for that one, LMFP. So it's an evolution of lithium iron phosphate as we know it today, but manganese has been chucked in as well. And the interesting thing there is that manganese is a cheap material at the moment, at least, and it's certainly pretty abundant. So the key there is you're maintaining the kind of cheap, ethical, abundant material kind of status of lithium iron phosphate, the safety, the longevity, the advantages of lithium iron phosphate that have resulted in it being adopted in the likes of the standard range Tesla Model 3Y, BYD's electric vehicles, and so on. But you've added manganese in there to give a modest boost to range and also, allegedly, to cold weather performance. Lithium iron phosphate doesn't like getting cold. LMFP doesn't mind it as much, so you don't get as much of a range drop. I mean, this tweak on LFP is rumoured to be able to give a range of getting close to 300 miles per charge out of the standard range version of the Model 3. In other words, the entry level one that doesn't have as much range as the long one. That's getting close to long range territory in its own right. So yeah, this could be a serious game changer, which would potentially dent demand for nickel and cobalt, but manganese would still be right up there.
LMFP sounds like LFP has discovered its perfect seasoning that could allow it to gazump NMC on energy density. But if all those chemistries are concerned with squishing more lithium into the cell, can they be combined to get a pick-and-mix battery pack that perfectly suits the specific application?
Practically perfect in every way.
Fundamentally, you could combine some of these technologies. So, for example, the initial versions of solid-state cells, some of which might not use lithium foil or lithium or anode-free, I should say, designs. They might still use graphite. Similarly, they might use silicon. Who knows? There's also the possibility of semi-solid, as I mentioned, where you have your solid-state electrolyte, but then you have some liquid in there as well on one side to help to improve the conductivity, if you wish, of that setup, to allow the lithium ions easier access in and out of that electrode, and then obviously through the solid electrolyte to the other side. There's various things you can do like this. And of course, whilst we've been focusing on conventional sodium ion, it's only a matter of time, I suspect, before we start looking at the possibility of using sodium anodes, pure sodium anodes, or even kind of trace emining it with an anode-free design on that. Solid-state electrolytes for sodium ion. There's various different ways that you can combine an anode, a cathode, and an electrolyte.
We don't just have to back one horse, and the chance to combine chemistries means we can optimise battery packs for each and every application. So with that in mind, do we need 1,000-mile batteries? Is that fundamentally a silly question?
So anyone listening in Europe at the moment is probably thinking, no, that's just silly, because the distances that we drive aren't insanely long. I mean, 1,000-mile battery, that's John O'Groats to Land's End in the UK, and plenty to spare. So yeah, do we really need that? I mean, for a start, your bladder would have exploded by the time you'd driven that distance. So to be honest, there should be more focus on making sure that there's the trunk road rapid charging infrastructure available where you need it, and even better, charge points at destinations, whether it's shopping centres, whether it's hotels, whether it's tourist attractions, offices, and so on, because your car probably spends about 95% of its time sitting still. Obviously, there are some, like taxis and so on, where they're on the road a heck of a lot, but the driver eventually needs to stop for a break, and if you can rapid charge within the dwell time of that break, and for logistics within the driver's taco break, then that's all we need, really, and it saves precious materials that can be used to electrify other vehicles. For the North American market, there may be some extreme examples where a 1,000-mile battery is needed, but certainly not in a passenger car. I very much doubt that, unless you are looking at the extreme wilderness of Canada, for example, when you're heading really north, when you've come off of the only road, kind of gone north, that's where things get interesting. There's less charging infrastructure. But again, wouldn't it be so much more simple to install a 7 kilowatt charge point at your destination up there than it would be to have 3 to 4 times the range that your vehicle realistically needs? So there will be some applications where it's required, particularly shipping, aerospace, that sort of idea. Intercity buses, maybe, but again, you'd be stopping eventually, not least because the passengers will need to stop for a whiz and a sandwich at some point. So yeah, do we really need a 1,000-mile battery? Not for a conventional car. Very much doubt that. And in fact, the situations where you would genuinely need a 1,000-mile range are very, very niche. And they'll be supported, but for mass production, no, but we'll probably be using these new chemistries we discussed today to make the vehicle cheaper, lighter, more efficient, more ethical. That's the way it's going.
So how good will batteries get? Well, as ever, the answer is it depends. Want cheaper batteries? Then perhaps back sodium ion. Want that illustrious 1,000-mile range? Then maybe hold out for solid state. Or if you want to go further with a smaller battery pack in the nearer term future, then perhaps LMFP or silicon anodes are the answer. And lithium sulfur definitely seems promising, although a little bit cantankerous. And of course, there are so many others as well, some of which we've featured on the show before. So to see the world's most power-dense battery, check out this episode on Niobolt. Or for a whistle-stop tour of the overall battery supply chain, then check out this one.